right, welcome back. So we have everything in place now to do orthographic projection, so we can implement games like this, but of course we also want to create really realistic graphics, which means we have to consider the perspective that we see when we look into the real world. So the step that is missing is to transform the view frustum to the orthographic view volume in a way that preserves the relative size and relation of objects to each other. So for example, if we draw it again here, if we have two identical triangles that are at a certain distance from the observer or the camera position here, then of course when we do them in the orthographic view volume, the one that is further away looks smaller. So if we get them in the orthographic view volume, the second one should be smaller and in the distance. So when we project it onto the screen, although they have the same size in the real world or in the 3D world, on the screen the smaller one appears smaller. So how do we do this transformation? So let's look into what is the characteristic of these points that are in our 3D space, how they have to be aligned. And so if you think about this is our I vector. It's an image from the book, that's why they use this different notation here, so don't be confused. This is our I vector, and we're looking onto a view plane. And then, so this is again just the top view to make it better, illustrate it better. And then, of course, the point that we see here at the screen is, of course, the first point we see when we follow this line here. Now, if that would be a transparent object, then, of course, we also see this object that is behind it. And in fact, we see all, if that is also transparent, if you only have transparent objects, we see all the objects that are behind here, all the objects that are on this particular line. And this is actually what we do in how ray tracing is done. If you remember the very first lecture, I gave an initial idea about how ray tracing works. We take a ray that we shoot from an observer to a pixel on the screen, and we follow that ray till the first object that we hit. And if we only have solid objects, then this is of course the object that we draw. If we have transparent objects, then of course we have to look into all the other objects as well. And now what we're doing for the projection is of course the opposite side. We go from the scene and we project it, and since we have this perspective projection, in the orthographic projection we would just use a direction, so we'll always project it in the same direction, but in the perspective projection we project it towards a target point, a viewpoint, which is the camera or the eye. So we project it along this line that goes through the eye from the object. And the point which we should draw on the screen is, of course, the intersection of that line with the screen. So if we project the objects, all objects that are on this line will end up at this particular screen. And that means if we want to transform this perspective projection to an orthographic projection that creates the very same image, that means, of course, that all points that are on this line have to be on this line that is parallel to the projection direction. Because for the orthographic projection, we project in this direction. For the perspective, we project in this direction. So of course, we have to move basically this line here. So we can think about this if you have a line here. Oops, that was here. Then we just have to basically rotate it around this point here to a line that is parallel to the projection direction for the orthographic projection that we want to have. And of course, we do not rotate the line, we rotate the points on the line to this one here. Now, if you look at the image here, this is what it actually does, but it looks a little weird here that the points are moving along this line here. Intuitively, you would assume if you do that the points are either moved directly down or that they are rotated in the same way as the line is rotated, but not just like jumping along the line as we see it here. But The problem is, of course, that when we do it with matrix multiplication, which is, of course, our ultimate goal to do this also with matrix multiplication, we cannot achieve this in a way that preserves the set order in the same way as it preserves the x and the y values. But the good news is we don't need to, because what we're interested in is the projection along the set axis. So the only thing we need to preserve is the order of the objects, because if I look at one line and then there are objects on this line and then I project them towards me, the only important thing is to know which object is in front of another one, because if it's a solid object I can see the one behind it. I don't see the one behind it. But it doesn't really matter if those objects have a distance like this or like this, because we're only looking into the projection along this line on a pixel level now, so it really doesn't matter as long as the order is preserved. And for that, we can create a matrix that does this transformation. In fact, the matrix that we'll have will actually transform the set value that actually works in our advantage, which we will see later. Good, so this is what we want. We want a matrix that puts the x and the y values from this line in the viewing direction to a line that is parallel to the orthographic projection and preserves the set order in a certain way. So the conditions that we have is we want map lines through the origin to lines parallel to the set axis. But that also, But that means, of course, parallel to the z axis. This is the z axis. Or if you're looking in negative z direction, it's minus z. Parallel to the z axis, that means parallel to our orthographic projection direction. But of course, like I said, we want to basically flip it around this point here. So that is, we also need to make sure that if a point is on the near plane, we need to map them. They should not change their position, because of course this line here would also be parallel to this line, but if we want to map this one here, it has to be rotate around this point here. So that is the second condition, that if they're on the near plane, they should be stay here. Another thing we have to be careful about is if a point is here, of course it should not move out of the view frustum. So points on the far plane should stay on the far plane. So the set value of those points should be the same, but of course the x and y values are different. And for all the others, so this is for the set value only, for all the others, the order should be preserved, but it doesn't really matter where they are along the set axis as long as the order stays the same. So we can have this, but this one should not go in front of the other. Good. And if we can do that, then we have here an orthographic view volume that preserves the relationships between the positions and the sizes and the objects in a way that we get the very same image when we do a orthographic projection than we would get with the perspective projection from the original view frustum. Good. So what kind of conditions do we have to fulfill for the x and the y values? So these are the conditions for the set values. Like I said, they are a little more flexible because we only need to preserve the order. But the x and y values, of course, they should be exact. And this is an illustration just for the y value. The x value is then perpendicular to it, but basically the same. And this is something where we look into basic geometry, where we look into triangle relations and sizes of triangles. If we have the I vector and then the viewing direction, and this is our viewing plane, and this is then a point on the viewing plane, then we say we want to map this line to this position here. So this should then also be ys. I call it s because it's the y value on the screen. And this is, of course, the set value. So this is x, y set. And that means the distance from E, because we moved the origin to E, is set. The distance to the screen we have specified when we know from the specification of the viewing plane. We know the y. We only don't know the ys, but we see from the triangle relationship that this distance divided by this one is the same as this distance divided by this one. So we have this relationship, which of course allows us to calculate our ys And in the same way also, of course, calculate our xs in the same way. Now, the problem with this is, of course, no, okay, just for the convention for the following, we assume that we're looking in the negative z direction. We could also do it in the positive z direction. We just need to be sure that it just changes the calculation a little bit from the signs, but we just need to be sure that that we're not crossing the origin, because if we're crossing the origin, we get some artifacts, but it doesn't work out anymore. But otherwise, it's just the convention. If you're looking in the positive or negative z direction, we just assume the negative z direction here, and we assume that we're projecting onto the near plane, which does not necessarily have to be, but of course that makes the calculation a little easier, because otherwise the viewing plane would be another parameter in between. So we just assume now that we're projecting on a near plane, so a near plane is basically our screen. That means we get rid of the distance, and the distance is just minus n, but because we're looking in the negative z direction, it basically is this equation here, just the d replaced by an n. So this is what we need to calculate here. And of course, we have to fulfill the set values have to fulfill this condition here. And the problem is now, of course, you see we divide here a coefficient by another coefficient. And if you remember matrix multiplication, how it works, it should be clear that this doesn't work out. Because with matrix multiplication, you get something like that. So you will never be able to produce a result where you divide one variable by the other, because you will always get this linear condition here, this linear relationship between the coefficients. And that is, of course, why we can only use it for linear transformations. And of course, we had this situation before when we said we want to add a constant factor, because we've seen there that this also doesn't work with that, and the solution was to introduce these so-called homogeneous coordinates, because we saw that when we add another dimension here, and then d1, d2, d3, then of course we can multiply this, and then we can create this here, and because we have the zeros and the ones here, it doesn't change all the other values, so these stay the same. And that way we could combine this with our matrix multiplication framework and got these affine transformations, which were then the translation plus the linear transformation. And this is, of course, also how we are going to solve this division step, by this division problem, by saying we're extending again. In this case, we're not adding more homogeneous coordinates, but we modify these homogeneous coordinates in a certain way that allows us then to do also a division by that depends either on a constant factor or on all three vector variables, vector coordinates that we have here. And with this way, by choosing the AIs, BIs, and EFGs and Hs appropriately, of course, we could create something like that. So how can we achieve that? Well, the idea is basically, again, use these homogeneous coordinates, but instead of using a 1 at the end or a 1 at the vector here, we use just a different value, and when we later divide by this value. So we basically just use this spot that we have to drag this value with us, and then in the end divide by it, and that way we can create a division by choosing the coefficients appropriately. Then the y value will have exactly the values, create the values here that we want to divide by. So the idea is, compared to the homogeneous coordinates, in the homogeneous coordinates we said we have a point x, y, and z. We represent it by x, y, and z1, and that gives us the opportunity to create matrices that give us a translation. And now we say we have a point x divided by w, y divided by w, z divided by w, and we represent, no, yeah, that is a point, and we represent that by a vector x, y, z, w. So if we have a vector like this, it represents this point, but this vector represents this point, which of course for w equals 1 is exactly the same here. So we have exactly the same here. And that way, if we now create a matrix where we here not necessarily have only zeros and ones, we can create this vector here, but now we just have to be aware that this vector does not represent x tilde, y tilde, and z tilde, but it represents x divided by w, y divided by w, and z divided by w. And of course we choose a w in a way that in this case here it contains n divided by z, because then we can create what we need here. Yeah, and of course we also see if we keep 0, 0, 0, 1 here, then of course this w will be 1. So if we divide by 1, we will have the same result. So it fits into our framework, and it doesn't change our result if we use it in the matrices for if we apply matrices for linear and affine transformations, but it gives us the opportunity to also do this projective transformation that needs a division. So yeah, I already said that. This is the application to the linear and the affine transformation. But of course, when we do it for when we choose this EFGH not to be 0, 0, 0, 1, then we can create different values here. And then, but then of course we have to make sure that in the end, before we use the point, before we actually draw it on the screen, we need to divide by this last value w here, which in this case of course then leads to the 1, and then we can use the homogeneous coordinates use it in the same way as we used the homogeneous coordinates before. And here it creates then whatever we want to create by choosing these AI and BI and CIs and EFGHs appropriately. And of course, how do we have to choose them to achieve this? That's now the big question. We do this by this matrix. So this is one of the matrices that achieves this result. Negative z direction, n and f are the near and the far plane, and we project towards n. Then this is a transformation matrix that does this transformation from the view frustum to the orthographic view volume. And we see that if we calculate it, so you see in this matrix here at the bottom, you don't have homogeneous coordinates anymore. That would be 0, 0, 0, 1. But we have chosen here this to be 0 and this to be 1. And here we've chosen these values appropriately to produce this result, which is x, y, then this more complicated, longer equation, z divided by n. Now if we do the homogenization, which is divide by w, in this case that means divide by w. That means in this case it's multiplied with n divided by z. Then you see we get exactly what we want for the x and y, exactly what we want here. And here we get an equation which, like I said, doesn't have to be the set value that maps the original position, but it just has to fulfill certain criteria, which are that the points on a near plane are mapped to themselves, which is obviously clear. If you look, this is here the target that we get with this matrix multiplication. And we see here if it's on a near plane, then of course z equals n in the original equation. And that means here n plus f minus f times n divided by n. That is obviously n. And the x and the y, of course, also stay the same. Points on the far plane, there the x and the y values change, but the z value should also stay the same. Of course, if we put f for z in this equation, this of course also leads to zs equals f, so this is also correct. Now another thing we have to check is, does it keep the z values that are in the view frustum or does it push them out or in front of the near plane? And that we can see again by this very simple proof here. If the z value is larger than n, then for zs we can have a lower bound, because if it gets larger, then this gets only smaller, which means if we set n here instead of z, we have a lower, an upper bound. So this must be larger than n. So this is correct. It stays behind the near frustum. If it is smaller than f, then the z value must also be smaller than f, so it must stay within the view frustum and not go beyond the far plane. And that is the same way here we get f can only increase, which means this will decrease, which means this will always be larger than f. So this is also correct. So the only thing we need to check is if the order within 2 points of the view frustum is preserved. And again, remember we're looking in the negative set direction, so these are all larger than 0. Again, it doesn't really matter if they're looking in the positive or the negative set direction. It just, if we're looking in the positive direction, the larger than 0 is on the right side here. But the important thing is that they are all either positive or either negative, because we want to see if a point set 1 is larger than set 2, then the projection of it should also be larger than the projection of the other. And that means if the difference of the two is positive, then of course this relation holds. So if we look at the difference here, this is just some simple arithmetic transformations. I didn't write down every single step. If you don't see it immediately, just write down each single step and you will see it's really just a simple arithmetic transformation that moves it into this relationship. And here we see, since all of them are negative if we're looking in negative set direction, or all are positive if we're looking in a positive set direction, this right side here, fn divided by set 1, set 2, will always be positive, because it's minus, 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 minus. And set 1 is larger than set 2. That was our major condition at the beginning. That means this difference is also larger than 0, but that means, of course, that the whole thing is larger than 0. And if it is larger than 0, then set 1s must be larger than set 2s. So this condition is fulfilled. So they really preserve the order. And like I said earlier, they preserve it in a way that is actually works in our favor, because if you look into this equation here, these are all constant values. So the only variable we have here is the set. So we have an equation here. We calculate the set s based on the set value. So it is proportional to minus 1 divided by set. So what we have here when we do the mapping is we have set mapped to set s by a function like this. And that means if we have 2 points here at the same distance of each other, these 2 points are mapped to this distance here, which, if I had drawn it better, would be much smaller than this one. And these 2 points, even with my bad drawing, you see, are much further away from each other. And this is why I said it actually works in our advantage, because if you think about what we have here, this is the direction in which we are looking. And now we map it to this direction here. Wait, no. Map it to this direction here. So you see, the points that are closer to us get further away from each other. The points that are further away get closer to each other. And that means, the problem is when they get too close to each other, you might run into rounding errors. And then, of course, you get artifacts that one pixel just sticks out because it's just not accurately. And, of course, if you have these artifacts, you want to have them at objects that are far away, because they are so small that you hardly recognize those artifacts. But the closer an object are, the more likely it is that an observer sees those artifacts here. So the accuracy improves actually when it's closer to you and decreases when it's further away from you. And that is actually something that can work in our advantage. And this is why this mapping, although it is not the one you would intuitively assume as the best, is actually in practice better than the other. And like I said, we cannot achieve it in another way with matrix multiplication, but this way it works. Good. Yeah. So, and this is then the final matrix that we get for this view box transfer, view frustum transformation, and then we can put this into. Wait, let's skip ahead here. can put this in our framework, and then we can not only do parallel projection, but we can also do this perspective projection. So we have everything in place, and we can do everything with matrix multiplication by single matrices or by one big matrix that we create based on multiplication of the individual ones. Now I skipped a couple of steps here because I want to look into this or explain into this extension of the homogeneous coordinates in a little more intuitive way, because I think this is probably the most challenging step from the whole mathematics that we have to understand, because the visual understanding of it is really a little more difficult, but there is also a geometric interpretation of it. I'm using a little different one here than it is in the book, so you can also read the one in the book. Maybe that presentation helps you understand it a little better. If you don't see it from here. So if you remember what we did with the affine transformation, how I introduced the affine transformation, I used a geometric idea behind it, which was the shearing at this level 1. And then I introduced the calculation. Here I did it the other way around. I introduced the calculation because geometric interpretation is also not really that obvious to understand, but it might help you a little bit, especially now that you know the arithmetic behind it. So if you remember what we did for the affine transformation, we said, okay, we cannot, if we in 2D we want to move an object, we cannot translate it with matrix multiplication. But if we are in 3D and have a copy, for example, at this plane z equals 1, then we can do a shearing, which is basically a translation at this level, and then we just project it down again, which if we're at level 1 just means remove the third coordinate, and then we have a translation in our original 2D space. And this is why we go from 2D to 3D with the homogeneous coordinate, or from 3D to 4D. And this was one of the images that I used to illustrate it, which I think intuitively makes it kind of clear. And then I said, okay, we can do this, of course, with all levels, but if we stay at the level 1, then we have these zeros and 1 in our matrix that do not affect all the other calculations, because every other coefficient is multiplied with 0, and only for the d's in the last column we have the 1 that adds it to them. And now I'm saying, well, just do something different in this last line, and then it will work out in the end. When I first heard this, I was kind of, how can this really work out? I purposely have chosen zeros and 1 and this 1 at the beginning, and now I'm saying do whatever you want, just as long as you divide at the end afterwards, it really works out. And but from a geometric understanding here, if you draw it from 1 to the 2D space, you can actually draw it quite nicely. And then you see that it actually also works from the geometric interpretation. So let's look into this, where like I said, because it's more complicated now, we go to the 1D and 2D case. So we have an object in 1D, and we want to translate it along this line, which is our 1D space. Then with the homogeneous coordinates, what we do is we add a second dimension, and we go from the point x to the point x1. So we are from here now. Then we do a shearing, which means we add the d to the x. And then, of course, we do project it down by just removing the third coordinate. And then we moved the point x to the point, or we transformed the point x to the point x plus d with a matrix multiplication, which is, of course, something we couldn't do before. Now, what I'm saying now is when we have here different value, when we have a matrix that doesn't have 0, 0, and 1 in the last row, but E, F, G, H, then of course when we multiply this with a vector 1, we get something that is different here, and that's, I called this a W. And then I'm saying, okay, now if we divide it by W, then of course we can, because this W can contain also these A, B, C, D coefficient, this X, Y, and Z values here, because we do not necessarily have zeros here. Like here the trick was to have zeros here to eliminate those x, y, and z. Now I have non-zeros here. That means of course I have this x, y, and z, but that's why here this here can depend on x, y, and z, and that's why I was able to create this divided by z here. Now the problem is of course when we do a translation now and we have this when we combine this, for example, with a translation where we have 0, 0, and 1, of course we're not changing this, but we still have then this w here. So how does this fit into the framework? And if you look into the visualization analog to here, when you have a point x and just for the translation you would move it in this level 1. Now what you're doing by multiplying it with a factor w is basically you represent this point not just by this one, but by every point that is on the line here. So this here is just times w, which is exactly here, where you get then a w in the last coefficient. And then, of course, if you do it like here, that you say, okay, now I do my division application, and now the matrix that does the division, and now I do the matrix that does the translation, and then you do the same as here, just project it down and by removing the last coefficient. Then of course you end up at a very different position than when you would do the translation here. But if you do this homogeneous divided by 1w, then the x and y coordinates fit again, because then you end up here at this point here at the level 1 again, and then you can do it here. So this is the geometric step you have to take, that here the point is represented by a point in that level, and here the point is represented by all the points that are on the line that go through this point at this level. And the slope of the line is of course then the factor w with which you multiply first and then later have to divide to get back to that level. And once you have this divided step, this step called homogeneization, here it is, then of course you are again at the situation where you have here the 1, and then of course you are in a situation where you can just use the x and y values like we did before. Good. So yeah, if it is a little confusing for you, like I said, there is a comparable but slightly different explanation of the geometric interpretation also in the book, so you might want to check that. Also, if you look at the image maybe at the end, and without all the scribblings that I did now, then you can probably understand it in a better way, hopefully. Good. Another thing is important characteristic is this is like I explained it right now. Now, if you think about what happens if you make a scalar multiple of this matrix, then of course you get a scalar multiple also here. But then if you do the homogeneization, it still works. So you still get the 1 here. You just have a scalar multiple here. So this is just c times, oh no, it's not c times, the c value gets out here, which means that not only this is a projection matrix, but any matrix that is just multiplied with a scalar multiple is also a correct perspective transformation matrix. And the reason why I'm bringing this up is that this is the one used in the second edition of the book, and this is the one used in the third edition of the book. So if you're working with the second edition of the book and you see there are different transformation matrix than I used here, don't be confused. It's not a mistake. It's just one of the different ways to represent it. If you work with the third edition of the book, you also should be confused when you see one of the equations later at the bottom, I think, of the page it is, because there is actually a mistake in the book, and that is basically, I think it's just a copy-paste mistake from the second edition. They changed the transformation matrix, but forgot to update one of the equations. So in one of the equations, it's actually the you see that they actually use this equation, perspective projection matrix from the second edition, which is why the equation contains a mistake. So make sure to check the list of errata on the book's website. And if you do that, then you will actually see that a student from this course actually found this mistake. So we are famous there listed. Good. All right. Yeah, and then we have everything in place and can implement it to do the projection, like I said, with these points here. So what we can do is now create wireframe models, but of course, if we have a wireframe model, then it doesn't matter if the object is behind it, because we can always see through the model, and we want to see also the wireframes of the models behind it. But of course, if we do the shading, then the object behind a solid one should not be visible. So we have to deal with that, and also we have to deal with the case where objects are only partly within the view frustum, because they need a special treatment. And what else is it that we have to deal with? Yeah, of course, the actual shading and the texturing. We talked a little bit about this already, but we will do more in detail later than in one of the next 2 lectures. Good. So, any questions? Then we're done for today.